Okay, folks, this is the second half, so we're going to do questions 5 to 8 of this week's work. So it's 1-bromobutane and KCN in aqueous ethanol. So 1-bromobutane is CH3, CH2, 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 Br plus KCN. And like I say, potassium cyanide, there's only one mechanism you know it to be used in at the moment, which is nucleophilic substitution. So what will happen is the cyanide ion will swap the bromine and you end up with CN and KBr. The name of this particular molecule, you'll notice that we've gone from 1-bromobutane, which has got 4 carbons in it, to something which has got 5 carbons in it. So it's a very important process for lengthening the carbon chain. Potassium bromide as our byproduct. So the mechanism there is my 1-bromobutane. I'm not going to show you. In fact, no, I will show charges this time. So bromine is more electronegative, therefore has a partial negative charge. The cyanide ion, which is our nucleophile. Alright, make sure the lone pair's on the carbon, not the nitrogen. You don't have to show the triple bond. I've just done that to show you that it is actually a triple covalent bond. And then curly arrow. Backside attack, or front side, doesn't really matter, and you end up with the pentane nitrile. And the essential conditions, like I say, are already in the question. The potassium cyanide has to be in aqueous ethanol for this reaction to be feasible. Okay. Right, so we'll look at question 6 now, which is the chloroethane plus potassium hydroxide in alcohol. So chloroethane plus potassium hydroxide in alcohol. So 6 chloroethane. And because it's in hot alcohol or hot ethanol, it is not nucleophilic substitution, it is the elimination mechanism. So you end up with the alkene, which will be ethene in this case, plus water plus potassium chloride. So it's 3 curly arrows for this one. Again, I'm drawing my hydroxide ion back to front just to show that it can be done that. If you do, just make sure that the lone pair is always on the oxygen. Negative charge can be anywhere on it, but again, for accuracy, I'm putting it there. And then it's 3 curly arrows. Bingo, bango, bongo. And so this hydroxide here is taking a proton, so is acting as a base. And then the electrons in this carbon-hydrogen bond form the carbon-carbon double bond, and the carbon-chlorine bond breaks there to leave a chloride ion which will bond with the potassium ion and make potassium chloride. So this mechanism is elimination, or sometimes called base elimination due to the role of the hydroxide ion within it. And like I say, if it wasn't in hot ethanol, the potassium hydroxide, if it was in warm water, warm aqueous, you'd end up with nucleophilic substitution, which means the hydroxide ion would be acting as a nucleophile instead. Okay, right, so number 7 is the dehydration of pentanthreol. So, dehydration of pentanthreol. Okay, so pentanthreol I'm going to do the mechanism first, I think. Okay, so when you dehydrate an alcohol, a couple of things to take into account. Firstly, you lose the OH and a hydrogen from the carbon next door. Now, you've got to be careful here in this particular reaction, because you could end up with two different products, but due to the line of symmetry, sort of down the middle there, it doesn't matter whether we take that yellow hydrogen there or this blue one here. Okay, so have that form as water. You'd end up with the same product each time. Okay. Ooh. So let's have a look then. Okay, so first things first, it's an acid catalyzed reaction. So I'm going to get my H plus ion again, put my lone pairs on my oxygen, and this will form. I'm going to do a bit shorthand now to speed things up. And then to form the product, we can do it in one foul swoop. So the double bond we know is going to form there. So this H will fall off in the form of H plus, regenerate our catalyst, and then that will fall off as water, giving us this product here, plus water, plus the H plus, which is regenerated as our catalyst. Can we name this particular product over here? Loads of people would name this as pent-2-ene, and obviously these people would be incorrect, because clearly you hopefully can see there is a form of EZ isomerism going on, and if you were to bend these bonds around a little bit, you would see that the methyl group and that ethyl group, which are the two priorities and highlighted in blue on either side of the double bond, are on the same side, so it will be Z pent-2-ene. So again, conditions, just heat it with the catalyst, which is conch sulfuric acid yet again, and you end up with the alkene Z pent-2-ene, and you could also end up with E pent-2-ene as well. Okay. Right, last question is the equations and conditions for the production of ethanol. So two ways of making ethanol. So I'm just going to draw ethanol in the middle of the page, and there are two ways of making it. One is the hydration of ethene, and one is the fermentation of glucose. Okay, so hydration of ethene. We looked at the hydration mechanism earlier. Okay, you can do the mechanism if you want. I'm not coming to it at the moment, just to save a bit of time. Essential conditions, like you say, you'll need a temperature greater than 100 degrees Celsius. So you'll also need a reasonably high pressure, but key thing is you'll need a concentrated phosphoric acid or sulfuric acid catalyst. Interesting points about this, so I'll do this at the bottom here. You'll notice that there's only one product, so it's 100% atom economy, so very well, no waste. It is a very fast reaction, but unfortunately it's also very expensive. because the ethene comes from something called crude oil, or actually it's made by the cracking of crude oil fractions, the catalytic cracking of crude oil fractions, that is. So it's a finite resource. Okay. If we look at the fermentation of glucose, becomes 2 lots of ethanol and carbon dioxide. Conditions for this then needs really, you need yeast enzymes for your catalyst. So they are biological catalysts, so they'll work best at a temperature between 30 and 40 degrees Celsius. It needs to be anaerobic as well, so no oxygen. That will help prevent the ethanol from oxidizing further. And also it's what conditions the yeast need to be in to actually carry out this fermentation. And another one is it needs to be in aqueous conditions. So it needs to be in aqueous conditions for this to occur. Interesting points about this reaction then. Obviously it's renewable resource, so glucose can be extracted from plant sugars. It is a lot slower, but it could be argued that it is carbon neutral. So it's a carbon neutral fuel. So if you were to take all this ethanol there and burn it, so in an internal combustion engine, let's say, and we'll assume complete combustion, even though in reality it probably wouldn't, you end up with 4 CO2 and so 3, 4, 5, 6, 12, 6 H2O. So that's 8, 14, 6 O2. All right. So why could this be argued to be a carbon neutral product? Well, if you have a look at the amount of CO2 produced so far, we have produced 2 moles of CO2 there and 4 moles of CO2 there. So 6 moles of CO2 has been released to the atmosphere in total. But let's look at where the original glucose came from. It came from a process called photosynthesis, which is 6 CO2 plus 6 H2O makes glucose, 1 mole of glucose and 6 moles of oxygen. So you can see here that, there we go, 6 moles of CO2 were taken in by the plant originally, and those 6 moles of CO2 were released upon processing of the glucose and burning of the ethanol produced. So that's what carbon neutral actually means. There is no net gain in atmospheric CO2. I said potentially carbon neutral because obviously you need to harvest the crops, you need to transport the glucose, etc., etc., and even generating temperatures of 30-40 degrees Celsius possibly relies on fossil fuels being burned at some point. So unless they're being run on biofuels themselves, I wouldn't necessarily call this whole process carbon neutral, but it certainly is more beneficial to the environment than the combustion of petrol, for example. Okay, and that concludes this week's lesson.